I swear I'm not trying to draw the series out for longer than it has to, but as time goes on, I realize that there is one more aspect to 3D collisions that I have yet to talk about, and it's fairly important. So right before I end things off, let's do that. Hello all the crazy people out there, my name is Michael, I like wizards and dragons and making games, and let's talk about sphere displacement. So you can do this with other shapes, but I'm just going to deal with spheres today because it's going to, well, the math for spheres is simpler than for other shapes. Doing this with other shapes starts to get into the territory of physics responses, and I long ago decided that physics responses were out of scope for this series. So let's say you have a character, and that character is represented by a sphere to make things easy, and I'm going to draw a little picture, and we're going to be, I'm going to illustrate what we're about to do before writing any code. So that is our player. That's not a very good player. Might be a little more potato-shaped than sphere-shaped, but it'll do the job. Alright. That's our player. And let's say that we have something like a wall. And let's pick another color. Let us make the wall, I don't know, a red or pink or something like that. Alright, that's our wall. So if the player is moving towards the wall, the way that you would generally handle this in GameMaker, I'm like the vector of motion like purple or something. The way that you would generally handle this in GameMaker would be something like the Sean Spaulding collision code. You iterate over the distance between you and the wall, or you and the distance that you're going to move one step at a time. So if you don't find a collision, you take another step. If you don't find a collision, you take another step. If you do find a collision in your next potential movement step, then you decide that you can't go any further, and you go back to your last safe position. And that is good for basic use. It'll get the job done, but it has some problems. The first one that people tend to run into being that it is one collision check for every unit of distance that you are moving. And if you're moving, say, 10 pixels per frame, 10 units per frame, then you have to do 10 collision checks. And honestly, in 2D and GameMaker, that's alright, because GameMaker's 2D collision system is pretty dang fast, but in 3D, it's suddenly a lot more complicated for various reasons. We're going to talk all about optimization next week. And if you have to do 10 collision checks every time you move, then that is going to be a decent chunk of frame time in any moderately sized 3D world. And especially in 3D, you also have well, this can happen in the 2D platformers that people make in GameMaker too, but it's a lot less noticeable. But in 3D, you start to notice the problem of what happens if the last safe position based on your movement is actually a little bit away from the wall, and you're not actually like touching the wall, which is where you would usually want to stop. And you can run into some annoying situations, and this can honestly manifest as all sorts of problems, but you can run into some really annoying situations where you can get sort of close to a wall, but you can't actually get right up to it, because the distance between you and the wall is smaller than that step size. You can run into some annoying situations where like you get stuck on corners in awkward ways because, again, the step size. And with some clever workarounds, you can mitigate those issues. But what if, for example, you were to start out at your original position and then you were to move to your final position, which may or may not be inside a wall. And then if you're in contact with the wall, you would figure out how much you have to move if you wanted to stop being in contact with the wall. And that is what the concept of sphere displacement is all about. This will, as a bit of a happy coincidence, also handle some situations that you might otherwise have to code yourself, such as if you wanted to move up to the wall and then slide against it. Sphere displacement should handle that without any extra work. I found that this handles corners somewhat better than the iterative process of collision checking does. So let's deal with sphere displacement. So first, I'm going to write a few methods in the various collision shape classes. They're going to be about displacing spheres, so when I move into contact with another collision shape, we are going to draw a secondary sphere at the point of contact, or at the displaced point of contact between the sphere and that shape. So it also works for corners, as I said. So if I were to let me try and hit this corner up here. If I were to move up and down around the corner, the displaced sphere would appropriately be shown around the corner. Let me get that on the corner again and hide the original shape to see. Perfect contact with the corner. And then after that, I'm going to bring it into the test world, and we're going to see how our iterative collision detection can be improved by dealing with sphere displacement. So again, you can do this with other shapes, but it will be significantly more aligned with like physics responses, so I'm not going to do that here. I'm also not going to handle a couple of other specific situations because, as you can probably imagine, this rabbit hole does go rather deep, and I'll be honest, I just want this 3D collision series to be over with already. So, some changes to the main 3D collisions project I've made. One, if you hold the Shift key on the keyboard, shape 1 is not going to be drawn. That is so that we can hide a sphere and so that we can only draw a potential point of displacement. And 2, when shape 1 is a sphere, I'm also going to be getting the result of a method which has yet to be written called Displace Sphere. And it's going to take a sphere as a parameter, and it's going to produce a vector 3. And that vector 3 is going to be the position of the sphere if you wanted it to be displaced from within the shape. It'll also return undefined if there is no displacement is possible. We'll talk about edge cases when we get there. Another change that I'm going to make before I do anything else, and this is one of those little decisions that I made way back in the beginning that kind of may have come back to bite me more than 2 years later. But as a general convention, I have set it such that if if you have a point in a sphere, or if you have 2 spheres, with sphere collision checks in particular, and I think I did this with some of the other shapes as well, but if the sphere is exactly touching the surface of another shape without actually having an intersection with the surface area, I still count that as a collision. So you can see here, point and sphere, if the point's distance to the sphere's position is less than or equal to the sphere's radius, I'm counting that as a collision. And all else being equal, you could make an argument for why it should be that way, but that is going to cause some problems for us when it comes to displacing spheres, because we are going to attempt to move a sphere out of collision with another shape such that it is exactly touching that other shape. And under the system that I have now, when a sphere is exactly touching another shape, and this is going to be particularly important when it comes to the box shapes and like planes and that sort of thing, that would still count as a collision, which will cause some issues for like actually using this in a game. So I'm going to go through my code. I'm going to remove, when it comes to spheres and I guess also other shapes, any less than or equal to's or greater than or equal to's that pertain to a radius. I'm going to change that to less than or greater than without the equal to. And it'll take me a minute to go and track down every situation where I'm doing that. For now, I think I'll just do that with spheres, because what do we have, like 50, 60 shape intersection tests, and I don't really want to have to check all of them right now. So spheres and points, spheres and spheres, spheres and AABBs, spheres and planes. Any others here? Spheres and triangles. I'm going to also want to check capsules, OBBs. Meshes and models are kind of different because they are composed of triangles. Lines, spheres and lines. We can get rid of the less than or equal to there. Check ray, I don't think has this problem. So what else did I say? OBBs and capsules. Let's look at spheres and OBBs. And let's look at spheres and capsules. I suspect, yeah, capsules are also going to have this problem. I guess while I'm here, I might as well delete the less than or equal to's between like capsules and points. Spheres, of course. If I had thought 2 years ago that I was eventually going to include shape displacement in the series, I probably would have just done it like this in the first place. Hindsight's 2020. I hope this isn't going to be like a deal breaker for anyone who's using the system. Let's commit that. So I'm going to start, as usual, with points when it comes to displacing spheres. As usual, this isn't something that's going to be directly useful very often, but it is going to be a easy place to start that I think will make explaining the other shapes a little bit more straightforward. So before I write any code, let's talk about some of the edge cases that will just return undefined instead of returning a vector 3 of the displaced location. One is going to be if the shapes are not actually in contact with the sphere, so if the sphere is not colliding with the wall or another NPC or whatever it happens to be, then there's really no point in trying to displace the sphere from that shape. The easiest way to do that would be to say, let's say, if not self.check sphere, then just return undefined. This is going to be a bit of a common refrain in a lot of the sphere displacement checks. Another edge case in which we won't do anything is if the point is located exactly at the sphere's origin, then the math kind of breaks in that situation. So if we try to find the shortest displacement of the sphere so that it's not in contact with the point any longer, then you could push the sphere in literally any direction. And you could totally just pick an arbitrary direction and give the sphere a big old kick in that direction. But instead, if self.position.distance 2 sphere.position equals 0, then we are going to return undefined in that case as well. Otherwise, if neither of those edge cases are met, we can find the direction from the sphere's position to the point's position. We can do that by saying sphere.position.sub our own position. We're going to want this to be a vector with a unit length of 1, so let's normalize that. So this is going to be a vector 3 pointing from the point to the sphere's center. That is going to tell us essentially which direction we're going to want to kick the sphere. And the amount, so the distance that we are going to have to displace the sphere from the point in space is going to be, let me call it offset. That is going to be the direction multiply by the sphere's radius. This is going to give us a vector 3 in the direction from the point to the sphere's origin, and it's going to have a magnitude of the radius of the sphere. And so if we were to add that offset value to the position, then that is going to give us a vector 3 at a point in space that is exactly the sphere's radius away. And if you put the sphere at that position, then it will have the point be on the surface of the sphere, and that will also be the nearest point that you could possibly displace the sphere to, so that it is that is going to be the nearest to the sphere's original position. So if I were to run the example program now, we have two spheres. If I were to summon a sphere, and if I were to offset a little bit, you saw, by the way, that when it's on the origin, when the sphere is perfectly on the origin, we're not having that green ball appearing anywhere, because that's going to be our, I guess you would call it a degenerate case, and we're returning undefined. But if I were to move the sphere out a little bit, say out to the right a little bit, you can see that the green ball, which is our displaced position, is going to be exactly in contact with that point in space. And as a friendly reminder, the little green ball representing the point in space, this is a sphere with volume itself, but we're just going to pretend that it's an infinitesimally small point in space. It is somewhat larger than infinitesimally small because I still want to be able to see it when I'm doing tests with this. And if I were to move the sphere back in pretty much any direction, even if it's at an angle, even if it's up or down a little bit, we can see that we are still going to be able to displace such that the displaced sphere is exactly touching that at that point. So that is displacing a sphere from a point. From here, it's probably pretty easy to imagine exactly how displacing a sphere from another sphere is going to work. So if I just copy paste this, drop this at the bottom of the collision checks for call shape sphere. So once again, our first case that we're going to return undefined if the two spheres are not actually in contact. Our second case, our degenerate case, is going to be pretty much the same. If the sphere's position and the other sphere's position are exactly equal, then again, you could pick any direction arbitrarily and give the one sphere a kick in that direction. but I'm just going to return undefined. I don't know why I'm using like the kick idiom so many times in this video. I guess I'm pretending that the sphere is like a basketball and the thing it's colliding with is my foot or something. By the way, don't ever play basketball with me because I don't know any of the rules. Anyway, everything else is also going to be pretty much the same as displacing a sphere from a point, but instead of offsetting by only the incoming sphere's radius, we are also going to add the other sphere's radius. That's pretty much like geometric canon, is that the only interesting difference between doing any of this with a point and with a sphere is that points are basically spheres with a radius of 0. So let us run this. I'm going to summon a sphere. I'm going to summon a second sphere. And if I were to move the one sphere around, we can see that our green displaced sphere location is, as before, going to be perfectly in contact with the other sphere. And in kind of the same way that the points that I'm drawing in here aren't like geometrically perfect points because they have to be big enough to be able to see, these spheres aren't geometrically perfect spheres either because they are composed of polygons. So you'll just have to imagine that these two spheres are like perfect shapes and that you can't actually see daylight between them. Anyway, that is going to be displacing a sphere from another sphere. So I'm actually going to skip AABBs and OBBs for a bit, and I'm going to come back to them later. Those shapes are going to be a little bit different, although very similar to each other, and I do want to cover some of the easier ones first. So next, it's open over here. Let's go to capsules next. Capsules, of course, are just long spheres. That's the real reason I'm dragging this series out, because I want more excuses to make that dumb joke. Anyway, so we, our degenerate case for capsules displacing spheres is going to be a little bit different, because we can't simply say the distance to the capsule's origin to the sphere's origin, because the capsule's origin is more of a line. But we can say the nearest point between the capsule's central line and the sphere's position. And instead of this, we can say if nearest.distance to sphere.position equals 0, we can return undefined, and that is essentially going to accomplish the same thing as this was with the other two shapes. Our direction, once again, is going to have to be a little bit different. So instead of getting like sphere's position and subtracting the point's position or whatever for the direction, we are going to use the nearest point on the central line to the center of the sphere, and we are going to use that as the quote-unquote position of the capsule. And following from there, we are going to proceed as before. So sphere's position, subtract that, normalize that, unit length of 1, take that that normal and multiply it by the sphere's radius plus the capsule's radius, same as before. And we are going to add that to, instead of self.position, because we don't have one, the nearest point on that central line. And that should give us capsules displacing spheres. So let me run this. Let me summon a capsule. What number is that going to be? Number 9. And a sphere. So let me get a good look at that. So if I move the sphere out to the side a little bit, we have our point of displacement. If I were to move, for example, up or down a little bit, we still have our capsule. I should find somewhere better for this text to be instead of right in the middle of the screen. We're going to have our sphere being displaced from the capsule up in one of the end caps. We could also move around to the other side. It would help if I allowed the sphere to be visible. We can circle around the capsule. Right? And that is going to be displacing a sphere from a capsule. What do I want to do next? Let's do planes next. Planes shouldn't be too hard. So you're probably noticing a bit of a theme in the way that we are displacing a sphere from a shape. So we are going to find, in some capacity, the nearest point between the center of the sphere and the shape in question. We are going to find the normal of the shape in question at that nearest point. And we are going to move the sphere some distance away from either the center of the shape in question, if it's one of the rounder shapes, or away from the point of contact on the surface of the shape. So yeah, let's do planes next. Let's go to the bottom of the check line code, stick our display sphere code down here. Planes have a nearest point method, very convenient, so we can do something a lot like what we did with capsules, and instead of saying self.line.nearest point, that's just going to be our own nearest point to the sphere's position. The degenerate case here actually does not apply. If the sphere, even if the sphere's origin is perfectly cutting the plane, then we still know the normal of the plane at that point, and it's not going to be either undefined or non-existent or literally whatever you want, the way it was with some other shapes. So I can just delete that, and I can basically continue as normal. So our direction, or I guess at this point you could just say the normal, is going to be either the sphere's position, subtract the nearest point on the plane, and you could normalize that so that it has a unit length of 1, or planes already have a normal. So you could say var dir is going to be self dot. Is it get normal or just normal? I don't remember. Oh, it's just a variable. Duh. So the direction could be that normal, or you could simplify this a bit and just say var offset is going to be self.normal.multiply by the sphere's radius.
Hey.
No need to add anything else to that because planes don't have a radius, and our final displaced position is going to be the that nearest point, and add that offset value. So there's a possible exception you might make here. So if I were to summon a plane and if I were to summon a sphere, if the plane is just if the sphere is just lying in the middle of the plane, you can see this is working correctly, which is pretty nice. If I move the sphere up or down, you can see that we still have our point of displacement perfectly touching the plane. If I were to move this down so that the center of the sphere is behind the plane, and like you only have a little bit of it poking through this side, the displaced sphere's location is still going to be on top of the plane, and that may or may not be what you want to happen. So if I were to go completely below the plane, it's going to disappear because we are no longer in contact with the plane in any way, and that's where we're returning undefined. You might, since planes are kind of like special, like geometric entities, you might consider, if the sphere is completely behind the plane like this, still displacing it above the plane as we had before. So you might consider writing a little bit of special code to account for the sphere being behind the plane like this. One can imagine where that would be useful if you have a plane representing the floor and you don't want the player to ever be able to clip through the floor. And if the player were for some reason to clip through the floor, you would want to just automatically push them back above the floor. You could make that argument. You could also make the argument that if... where is my sphere? You could also make the argument that if the sphere is below the plane like this, you should invert the normal and displace the sphere in the opposite direction. If you actually have, like, you know, gameplay happening on both sides of the plane, and like the bottom of the plane isn't out of bounds or anything like that, that might be the more desirable course of action. I'm just going to leave it like this. I think I'm going to invoke everyone's favorite phrase in math and leave that as an exercise to the reader. Triangles. Going to be very similar to planes. Triangles are, they do have some notable differences from planes, such as they are not infinite in any direction. They are bounded by 3 points. They are basically a surface bounded by 3 points. But for the most part, displacing a sphere from a triangle is actually going to be basically the same as displacing it from a plane. And there's a couple ways you could look at this, but let me start by just taking the displace a sphere from a plane code. And the only thing I'm going to change is from changing the like the plane had a variable that was just the normal of the plane, whereas triangles don't. Triangles have an actual Is it not down here? Is it at the top? Where is it? I know it's in here somewhere. Oh, get normal. It's right here. Triangles have an actual get normal method so that can be calculated on the fly. Otherwise, let me start this up. Let me summon a triangle. What's that? Number 4. Let me summon a sphere. And can I get a triangle that's like facing the other direction so that it's lit a little bit better? Are these triangles not lit? Did I like not include whatever? So triangles are also, they also have a direction. They also have a primary direction. The only reason that the up here double-sided here is because when they're drawn, I'm drawing them double-sided to make them easier to see. But if I were to move the sphere around on the surface of this triangle, up, down, left, right, whatever you want, we can see that we are being displaced some distance so that the sphere would be exactly touching the triangle. I'm not doing anything like fancy here. So if I were to move the sphere a little bit off the triangle like this, so that it's like cutting it on the side, our displacement location is not going to like wrap around the edge of the triangle or anything like that. And likewise, if I were to have the sphere behind the triangle like this, we are still going to displace it to the front side of the triangle the way we were with planes. I could see the case being made for that being the intended behavior of planes pretty easily, but I have a somewhat harder... Well, I can see more situations where you would not want that to be the case with triangles. So if you don't want that to be the case with triangles, then we can actually go back to what we had before with some of the other shapes. And instead of just using the triangle's normal or the plane's normal or anything like that, we could go back to calculating the direction pointing from the nearest contact to the sphere's position and using that as the direction that we're going to push the sphere. Again, triangles do not have a radius. That would be an interesting shape, to be honest, but in this system, triangles do not have a radius. Anyway, let me comment this version of the code out and run it again, and we are going to, 1, be able to wrap around the edges of the triangle, and 2... Oh, come on. Right, I also have to change that. We're going to be able to wrap around the edges of the triangle, and we're also going to displace through the front or the back of the triangle, depending on which side we're on. And let's see, if I were to move down, I'm having a real hard time with the controls all of a sudden. If I were to move down, we're going to be on the pushing the sphere through the one side of the triangle. If I were to move up, then we're going to be pushing the sphere through the top of the triangle. You can also see, if I can get it, why am I having such a hard time with these controls? If I can get it, oh man. I should be able to, there we go, wrap around the side of the triangle, as you would probably expect if you were to do this in an actual game. Not something you have to deal with planes, because planes don't have edges to wrap around in the first place, but when it comes to triangles, probably the intended behavior. So I'm going to leave this version of the triangle sphere displacement here commented out. If you do want it for whatever reason, it may be worth including like a configuration setting which version of the method to use based on your needs in the game. Like if you have a triangle mesh representing like the ground, the terrain, then you probably would be more inclined to try to always keep the sphere in front of the triangles. But if you have some other kind of a triangular structure, then both sides, the front and the back, might be just as well. Also, the degenerate case of when the sphere is exactly in the middle of the triangle, you might consider, in this case, not returning undefined, but just using the normal of the triangle. I think I'll actually... I think I'll leave a comment for that too. Anyway. So let's start to move on to some of the more complicated shapes, such as displacing a sphere from an AABB. I apparently don't have that open already. And this is going to work a little bit differently. So I'll start with our basic rules, and I'll say that, like, when we try to displace a sphere from an ABB, if the sphere is not actually in contact with the ABB, we're going to return undefined. If the sphere is located exactly at the center of the ABB, we're also going to return undefined. I just lost my place. But here the logic is going to take on its own a little bit, so I'm going to get the nearest point from the center of the sphere to the ABB. So far with the other shapes, or at least with capsules and spheres, if the center of the sphere has been inside the shape, then we don't really have to do anything different. It doesn't change the math. But here, when it comes to boxes, because we don't have a nice single radius to work with regards to the boxes, the special case of the center of the sphere being inside the box is going to make this a little bit harder. And there's a couple ways of going about doing it. One of them will definitely produce a better answer than the other. For now, I'm going to say if nearest.distance to sphere.position equals 0. And this is going to be the case if the center of the sphere is inside the ABB, because when we do nearest point over here, if it has to, it will return a point inside the shape, not simply on the surface of the shape. For now, I'm just going to return undefined. I'll probably come back and implement what I'm considering like the okay but not great solution momentarily. Otherwise, I am going to continue and save our normal is going to be sphere.position.sub nearest point, and we're going to normalize that. Was I calling this normal or direction? Should I keep it consistent? Let's call it direction. Actually, after this, we can just do what we were doing with some of the other shapes and return nearest.add the direction multiplied by the sphere's radius. This is going to be the easy case. If I were to run this, and if I were to summon a box, let's try and summon a bigger one. That one's sufficiently big. If I were to move these spheres so that it's in contact with the box, but the center isn't inside of it, we can see where our displaced sphere's location is going to be. If I were to move up, we're going to start to wrap around the top of the box, as you would expect. But if I was inside the box, if the center of the sphere is inside the box, it's not going to... I like to say the word degenerate. It's fun to say out loud. It's a fun sounding word. I should say it more often. Makes it sound like this Vector 3 like got in trouble at school or something like that. Anyway, so if you were to try and treat this case as you would the case where the center of the sphere is outside the box, then you're going to start to run into trouble, because if you just step through the math, sphere.position.sub nearest, if those two vector 3s are the same, then this is going to be the 0 vector, and when you try to normalize a 0 vector, you're going to suddenly do a bunch of 0 divided by 0, and you're going to have a bunch of nans popping up, and that has a tendency to break things. So we really do need a point that is on the surface of the box if we want to be able to do this correctly. And the easy way to do that would be to, instead of finding the nearest point on the box to simply the sphere's position, which we now know to be inside the box, what if we were to draw a line between the center of the box through the sphere's position until it was outside the box? So if I were to go back to drawing some doodles here, let me start off with another one. Find my pen. So if we have, let's say, a box. Oh, come on, what's wrong with me? If we had a box, and if we had a sphere, and I've drawn the center points of both of those shapes, just so that we can see where they are. What if, so that we had a point that was on the box that we could use to displace the sphere from, we were to draw a line out some distance, let's say over to over here, some distance outside the box, and get the nearest point from here to the box. And that would give us a nearest point on the surface of the box that's around here, which is indeed on the line between the center of the sphere and the center of the box. And if you were to think about moving the sphere to that point and displacing it from there along this line, pretending that's the normal, then you would end up with something like this. And that would give you a sometimes okay enough result. That'll be pretty easy to implement. The algorithm is basically what I said in English. The only sticking point being, let's save our new point. Actually, let's start with the direction to the center. And that can be defined by sphere.position.subtract self.position, so the box is center. Let's also normalize that so that it has a unit length of 1. Makes things very convenient. We can say our new point can be, if we were to take the direction from the center of the box to the center of the sphere, and multiply that by some arbitrarily large number. Let's say 1,000,000, or whatever number that is, I don't care. Then that'll give us a point that's probably outside the box, and we can find our new nearest point is going to be self.nearest point. And we can continue from there. Actually, if I were to just change the nearest point value over here, we would be able to continue as normal. This is just multiplying the direction between the center of the shapes by an arbitrarily large number. It doesn't sit well with you for a variety of reasons. Floating point errors coming from this number being too big, or what if you actually have a box that's bigger than that arbitrarily large value. Congratulations, you've been paying attention. A probably better value to multiply this by would be what I like to call the radius of the box, which I talked about this in one of the previous videos. If you have a sphere that circumscribes the box, that'll be a sphere located at position with a radius of the magnitude of this value. And if I were to say dir center.multiply by self.half extents dot magnitude, that looks a lot better, and that will indeed give us a point that is outside the box. You know it's outside the box because that is the distance from the center to any of the corners. And that'll be as good as any other point outside the box when it comes to getting the nearest. So let me run this. And this will, once again, give us a, 3? I'd like a bigger box. That's good. Anyway, this will give us an answer when the sphere is inside the box. And it looks like it's staying at the origin. Am I reversing something? Oh, the direction is reversed when I do this because instead of the sphere's position being outside the box subtracting the nearest point, it's the other way around, and that is having this vector be essentially reversed. Yeah, that's another step I should probably deal with. So we can say dir is going to be the opposite of that. Nearest point dot subtract the sphere's position. Else we can do what we were doing before. All right, let's try that again. I need a large box, which I can move around inside. All right, that'll be good enough. Let's move up. Sphere's position is inside the box, and we are sort of finding another position that is sort of outside the box, which we can displace to. You will notice some problems. This is not actually the nearest location which you could displace the sphere to. And by that I mean there is a nearer point to the center, or to the current position of the sphere that you can displace to that will be outside the box. In this case, straight up in the air. And another problem is if I were to not draw the original shape, you'll notice that this sphere is, it's inside the box. There's a part of it that's intersecting. And unlike before, this is not down to the finite resolution of the of the computer model. this sphere is actually inside the box. And that's not really something that you really want to have when you do this. If I were to move the shape around in different ways, you would see that it'll behave slightly differently based on like the exact nature of like the direction between the two centers of the shapes and that sort of thing. And in a lot of cases, it'll be like sort of displaced correctly, but also in a lot of cases it won't be. And that's if you're trying to have a character run around in the game, if you do something like this, you'll probably end up with like some weird cases where you like teleport around corners or something, which isn't really ideal. So what you really would want to do is, if we go back to our diagram over here, is instead of doing this, what you would want to do is you'd want to find the nearest surface to this point. It's going to be a little bit of work for AABBs, and it's going to be a little bit more work than that for OBBs. Also, this isn't perhaps the best example because the box is pretty like the sphere is pretty close to the corner. Anyway, if you were to draw lines from the sphere's position to the edge of the box and figure out which edge is closest and displace the sphere in that direction. Did I really draw on the wrong layer? It happens. Anyway, doing this would produce a much better answer. So if the sphere is buried a little bit inside the box on one side, and if you just displace the sphere based on that side, that'll produce a much better answer. There is still the corner of what happens when they are equidistant, and then you start thinking about actually dealing with the corners and wrapping the sphere around the corners. But this video has been going on for how long now? And I want it to be finished before never. You can hear my voice is starting to wear down. So I think I'm going to once again invoke the exercise left to the reader card here. And there's a couple ways you can do this. You can do it analytically. You can figure out with math the nearest point, the nearest side to the center of the sphere. You can kind of brute force it by doing raycasts in like all 6 directions and figuring out which one has the closest hit location. That's going to be a little bit less efficient, but it will be a fairly intuitive way to figure it out. I'm going to go back to making that a special case and just return it undefined. Lastly, when it comes to doing this with OBBs, once again, this is going to be pretty similar to doing it with an AABB. We're not going to, thank God, at least for what we have here, we're not going to have to deal with the axes of rotation of the OBB. Although, if you do handle this, case, you will have to deal with the rotation of the OBB to figure out the nearest side. And I'm just going to run the game. And I'm going to whip up an OBB. Again, can I have one that's a little bigger than that? Like, this is easier to demo when the shapes are a little bigger. Anyway, let's take a sphere. We can have it roll around the side of the OBB. We can see where that nearest point is going to end up. And we can see that, at least for the normal cases, displacing a sphere from an OBB is pretty much the same as displacing it from an AABB. So the remaining shapes, those being triangle meshes, transform models, rays, and lines, I am not going to implement, like, at all. Transform mesh, mesh, ray, and line. I'm going to just, I'm just going to point blank return undefined down here. Oh, come on. Check, check. Like this. For rays and lines, that's because this isn't really very useful and it's not something you're going to be doing very often. You could do it if you want to, doing something similar to what we did with planes and triangles, and find the nearest point to the ray or the line and just do it that way. Let's put that there. For triangle meshes and transform models, it's actually a fair amount more complicated because you do have potentially a lot of triangles on top of each other, and displacing the sphere from one triangle could push it into collision with another that it wasn't originally. And when you do that, you have to start dealing with how to sort the the distances to the different triangles and go with like the nearest one that won't put you in contact with another triangle or anything else. And partially for the sake of time and for the sake of this video going on for way too long, and I do want to do one more thing before I end it off, and partially because this is actually going to be fairly similar to that aforementioned thing that I want to do before ending it off. I am not going to do this now. If you're able to make sense of what we're going to do next, then you should be able to make sense of what you would have to do to make this work with a triangle mesh, and also a height map for that matter. I'm also not going to do this with a height map, at least for now. I'm just going to skip that one. And because you definitely can hear my voice is reaching the end of its rope today, I'm actually gonna put a pause on this and finish this recording some other day. And I am back. So the last thing that I'd like to do before I end this video is in much the same way that you can check not only two shapes against each other, but you can check a shape against the collision world as a whole, or an object against the collision world as a whole. I am going to write a little bit of code that allows us to run the sphere displacement check against the collision world as a whole. I'm going to start, I think, by going into the call object class and writing a static displace sphere method. It is going to take a sphere as an input. This is going to be a sphere shape, not an object. I went back and forth on whether or not there should be a shape or an object abstraction a little bit, but I decided that it would be a little bit easier to just go with spheres directly. And we can say return self.shape.displace sphere against the sphere in question. This is pretty easy. We're just calling the displace sphere method on the shape that we contain and returning the result. Next, I would like to be able to do the same thing against the call world data structure, one of the call world data structures. This is also going to take a sphere as an input parameter, and I'm going to have to make a couple other adjustments to some of the other code in this project if I want to do this. So the way that I initially designed it, checking an object against a quad tree or checking an object against one of the other data structures for the collision world, that's simply going to return a true or false, depending on whether or not a collision was detected. And for simple stuff, that's fine. But sometimes it might be nice to actually return a reference to whatever, at least the first collision object that you are detecting a collision against is. It is possible to be in contact with more than one object at once. You can over-engineer this to return an array, but that is going to be a little bit more work. So instead, I'm just going to return a reference to a single object, whatever the first object that we can figure out that you're in contact with happens to be, or undefined if no collision is detected. I am going to also, since this is recursive, instead of to handle the recursive result, I'm going to save the result of the recursive function call to a variable. If that result is not undefined, then we're going to return it, because that's an object. If it is undefined, we can't just return undefined, because we're going to have to continue on and check for collisions with the other nodes. This is the octree version. I believe the quadtree version is going to be basically the exact same thing. We can also edit the spatial hash code. The spatial hash check object, I think it is. If we save the result of this collision check, we can return the result if it is not undefined. We can return undefined otherwise. And I think I'm also going to have to scroll down to the spatial hash node and return a reference to an object instead of a simple true/false for the spatial hash node, and I think that's the last thing I need to change to make this work. Again, if I'd planned on doing this from the beginning, I would have designed it differently to begin with, but hindsight. Let me commit these changes. So the easiest way to implement this would be to say, let's say var collided with is going to equal self.check object. We're going to need this to be an object, aren't we, instead of just a primitive sphere, aren't we? I'll rename that to make it clear that this is supposed to be an object and not just a shape. And we can say if collided with is not equal to undefined, then we can return collided with .displace sphere, and sphere object.shape will be the actual call sphere that we're trying to displace. Otherwise, we can just return undefined. And this will work great if you're only ever in contact with one shape at once. However, if we go back to our diagram, can I get rid of like those green dots now? Let's say you have two collision shapes, and they're arranged something like this, and you're in contact with both of them at once. And let's say that when you try to displace yourself from one of these objects, you end up something like here. And if you were following this code that I just wrote exactly, without doing anything else, then you would find yourself in a situation where you are still, in fact, in collision with another shape, and there's nothing you can do about it because you're not checking for it. So it would be really nice if you could just in one move make sure that the game attempts to, if you're still in collision with some other shape, push you out of that collision shape as well. Something like this. So you've gone from here to over here, so that you're outside both of these collision shapes. And this is a lot like what would happen if you wanted to displace a sphere from a triangle mesh. You can imagine it would be very easy to be in contact with more than one triangles at once, potentially a large number of triangles at once. And if you wanted to implement displace sphere from a triangle mesh or a transform model, you would basically do something that would be a lot like what I'm about to do here. I will note that it is possible to put yourself in some cases where you just get stuck infinitely. For example, if you have two shapes like this, and you displace yourself from one, end up inside the other, displace yourself from the other, end up back where you started. And just by following this logic, it would be impossible to break loose without ending up in an infinite loop. Or it's possible that there is a situation where you don't get stuck infinitely, but it could potentially take a large number of steps to break free. Something like this. You try to displace yourself from one, end up inside the other. So you would go this way, then this way, then this way, and it would take potentially a large number of steps to break free. This might be a hot take, but I would say that if this ever happens, you need to find your level designer who designed your level where this was allowed to happen, and you need to ask them very nicely to change it. So in cases where we can't just go bang on the level designer's door and say, you deal with it, how do we deal with this? So we can start by putting this in a loop, and we can say, let's attempt to do this like 5 times or something like that. And instead of just checking once if we're in contact with something and displacing ourselves from it, if a collision is found, we can say attempt 5 different times to check for collision and then find a place to displace ourselves. Since we're now in a loop here, I'm going to reformat this code slightly. So instead of saying if collided with is not equal to undefined, I think it, this is my personal preference, but I think it is slightly more readable to take early exit conditions like this with either break or continue. I want break there, not continue. Because you know that there's no point doing anything further if a collision isn't found. We can also say instead of returning the value of the displaced sphere call, we can save this value like this. I need to get rid of that curly brace. And likewise, if displace position is undefined, we know that there's nothing further that we can do in this loop. We can break out of that. Maybe we're stuck inside of a box or stuck inside of another sphere or something like that. And if we do find a displaced position, what we can do is we can set the position of the sphere object shape of the sphere object equal to the displaced position, and then we can continue from there, use that as our new position, and we can check to see if there's any collisions or any potential displacements we can make from there. And we can run this in a loop 5 times, and then when we're finished, the sphere will hopefully be in a position that is no longer in contact with any of the shapes in the collision world. If it's a very crowded collision world, maybe the 5 iterations isn't enough. But we can return the sphere's new position as our location that we're going to displace to. Slight problem here, which is that we have modified the original position of the sphere, which preferably the internals of methods inside call world and whatever. Don't mess with the state of the world. They don't like change anything's position. It's just going to assess the situation and return a new position that you can do whatever you want with. To make that not a problem, you can either construct a new sphere and a new object to represent the sphere in the world. You can also help. You can also save the sphere's original position, which I think is what I'm going to do. Reset the sphere's position when you're done, and then simply return the displaced position. If the current position and the displaced position are the same, then you may want to ensure that that is that continues to return undefined.
Hey.
This is one of those ugly-looking bits of code that I wish I could think of a more elegant solution to, aside from constructing a temporary sphere and a temporary object. But I think that's just as awkward. Anyway, you may wish to parameterize the number of iterations in the repeat loop. You may wish to pass this in as perhaps an optional argument to the display sphere method, so that the user could specify the number of times that they want to try to make sure that the sphere isn't in contact with anything. Larger numbers will, of course, if you have a very crowded world, potentially make this take longer. A larger number of attempts will increase the worst case amount of work that this has to do. And lastly, we've implemented this in the call world class. We might as well just move it over as well into the spatial hash class. And, ooh, look at that raycast code. The logic is going to be the same. We have our check object. We have our collision shapes. Same logic should work regardless of whether you're using a quad tree or a spatial hash or anything else. So, the last thing I'm going to do before I end this video is I'm going to, once again, I'm going to bring the collision system into the test world, and I'm going to change the movement code in the test world. It took me a long time to find my my 3D collisions test world in my folder of GameMaker projects, but we're going to load up the new version of the collision system in the test world. I am hopefully going to demonstrate that this is going to make our lives a little bit easier and probably produce better results than what we had before. So this is not even Sean Spaulding's collision code in 3D here. This is really just we are going to check for a collision at the new position that the player is moving to, and if there is a collision, we're not going to move on each of the 3 axes. Gets the job done. It's not pretty. It doesn't really handle corners that well. It will not do things like handle slopes very well. If I were to actually, let me run this, and then let me change the collision shapes to OBBs, and we're going to see that this is going to be a little bit more awkward still than it would be before on OBBs. I don't remember if I made this change on camera, but I have I'm drawing the collision shapes instead of the 3D objects themselves in this test world, so that it's a little bit easier to see where the actual collision is happening. Remember, the player is a sphere, and the trees are all boxes. So this works. It doesn't handle corners very well. We can get stuck on those. If I were to change these to tree object, if I were to change these to, let's say, OBBs with a random rotation, something like this, I'm going to spawn them with a random rotation. I'm also going to reduce the tree count a little bit so there aren't quite as many trees in the world, because that might take a minute to start up with 1,000 OBBs being sorted into the hierarchy. Alright, GameMaker's new debug overlay is nice, but in the current version, it opens up, taking up quite a lot of space on the screen. In beta, it will start minimized, which is a little nicer. So you can see that when I hit the OBBs at certain angles, I just kind of get stuck on it because we're not really doing much to avoid collisions. If I were to, I can maximize this, I think. Instead of doing all this, let's see, the first thing I'm going to need to do is say, the sphere's position is going to be like, we're going to need to update the sphere's position. Let me comment out everything below this. That is handling Z speed. Actually, I'll comment out that for now, too. We can... we can call the display sphere method on the world with our sphere at the new position. We can say if this is not undefined, that can be our new player position. You can also say you can use the null coalescence operator for this instead of using instead of doing the undefined check yourself if you want. But while it's fancier looking, I don't want to make my code look weird for no reason. And when we're done with that, we can take our own player's position. I have not been super vigilant about using the self keyword in this example, have I? I believe for the Z position, I'm going to want to subtract 8 from that because the sphere is offset 8 in the air from the player's position. And we've now replaced a couple dozen lines of code with maybe 10 or so lines of code, and this should accomplish the same thing as we had before. Once it starts, all right, game didn't crash immediately, which is a good sign. I can still walk around. When I walk up to the edges of these OBBs, I turn around them appropriately. If I were to find a situation where there are multiple OBBs together, I still can't go through them or anything, but I will get stuck on both of them simultaneously. I will not ever become like stuck in between two of these shapes such that I can't move, which is good. Can I find two that are really close together, like these over here? A couple shapes that are really close together. All right. We can now go around these corners. We can not have to worry about rotation. We can not have to worry about any of the axes of rotation, messing up our potential movement. I don't have any examples of slopes here in this game, but if I did, we would be able to deal with slopes without really having to do much. I've disabled jumping in this example. That's still commented out. If I were to say, I think here, if I wanted to be able to jump, or fly in this case, I guess, I would still have to do a check to see if, like, I'm grounded or not. Something like what we were doing here, I think. So we're just going to check a small distance beneath the player's position. I think I might have copied the wrong line. And if there's a collision detected right beneath our feet, then we're just going to set our z-speed to 0. That's going to be jumping, flying, whatever. Let me run this. 400 trees that are OBBs are still kind of a lot, aren't they? All right. Oh, I also commented out the this bit. If you want to do something resembling gravity, you've got to actually, like, change your z-speed value over time. Anyway, we can jump, we can land on top of these AABBs. If I had multiple of these together, I would be able to, like, walk over them. We can also, like, sort of climb over them because of the shape of the sphere. But that is I don't consider that to be too much of a problem. And we have sphere displacement. Okay, I think we are done here. I hope this video comes out okay, because this has taken a very long time to put together. I kept, like, recording bits of it and then not being happy with the way it came out, so I had to do it over again, and it took a long time. You might have noticed that this was done over the course of, like, 3 separate days. And that's about how much trouble that was, and I hope that it comes out all right. I think we can safely delete that now. Anyway, that's sphere displacement. That's useful for a lot of things. Again, you can make this fancier if you want. You can make this deal with triangle meshes if you want, height maps. You could try to optimize the system by having the game prioritize which shapes get displaced from based on, like, which are closer to your original position or that sort of thing. That was Snitter's recommendation to me, but I don't want this video to be even longer, so I decided not to include that. I do look forward to, whenever I'm finally done with this 3D collision series and I get back to working on Wizard game, I do look forward to using this to make player movement in that game a lot less janky, and to make slopes work, and to make rounded corners work, and that sort of thing. And if you've watched the entire video, congratulations, and also thank you, and I hope that this is something that you can make use of as well. So, next time, optimizations, and then I'm never going to touch 3D collisions again. My name is Michael, I like Wizards and Dragons and making games. I try to post about 2 game dev videos a week, time permitting. I like to focus on the weirder things you can do in GameMaker, such as all this. So if you happen to be interested in the 3D shenanigans that you can do in GameMaker, feel free to subscribe. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. Otherwise, I hope you all enjoyed this, and I will see you all later. Special thanks to Army Armbuster, DJ Gibbles, Edward Holt, GameMaker, Manta Ray, Syndra Larson, Squarecrow, Vitro V, and Zenjament for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.